Hello students, once again this is your microprocessor teacher Ajay Sharma. Today we are going to read a very special IC that is used in the maximum mode of the microprocessors, that is 8253, commonly known as programmable interval timer. Now getting an idea or getting a concept what for this 8253 programmable interval timer is used along with the microprocessor is that this IC is used as a timer or the counter IC. When it is used along with the microprocessor is expected to perform several more important tasks such as processing, doing operations, addition, subtraction, the execution part, whereas it appoints this 8253 IC for its small operations like counting, producing delays, and for the timer purpose, right? This IC is used for this purpose. Now when we go further, let us see about its introduction. The Intel 8253 and the advanced version, that is 8254, are programmable interval timers, and these are designed for the microprocessor performing timing and counting functions using 16-bit registers. 16-bit registers means we are talking about the counters, and each of the counter has two input pins. One is the clock and the gate. Later we'll see these two pins in detail. Clock is something, the CLK, which we guys are using. This is the input from the crystal oscillator and the same input which is used by the microprocessor. And gate pulse is something which does the starting of the count. And one pin is for out. Once the counting is done, the output is generated via this pin. It informs the microprocessor that the counting is done. To operate a 16-bit count is loaded in the register, and on command it begins to decrement count until it reaches 0, and accordingly if we want to produce bigger delay, the bigger value of the count should be kept over there and it will starts counting back, for example 10, 9, 8, 7 and so on. Then it generates a pulse that can be used to interrupt the CPU. Now we'll see the basic difference between 8253 and 8254. 8253 happens to be the basic IC. Its operating range is between 0 to 2.6 MHz, whereas the operating range of 8254 is from 0 to 10 MHz. The basic 8253 uses on negative MOS technology, that is NMOS, and this one uses a high performance, that is HMOS technology. In 8253 the read back command is not available, whereas the read back command is available in 8254. What is a read back command? Later we will see in a detail. In 8253 it reads and writes of the same counter cannot be interleaved, whereas in 8254 the read and write of the same counter can be interleaved. Now coming on to the basic features of 8253/54, because we know there are very few petty differences between these two ICs, more or less the working and operation of both the ICs are very much similar. So the more prominent features are, it has got three independent 16-bit down counters. We have to note that any IC of 8253 has got three 16-bit down counters, and it can handle inputs from DC to 10 MHz. What is a DC? DC we are talking about 0 Hz. So from 0 to 10 MHz it can handle. These three counters can be programmed for either binary or BCD. BCD I think you know, that is binary coded decimal, and they all are compatible with almost all microprocessor. Almost all microprocessor, we are talking about 8085, 86, 386 and so on. The last feature says that 8254 has got a powerful readback command, which we have already seen in the last slide, the differentiation between 8253 and 54. This is called a readback command, which allows the user to check the count value, the programmed mode and the current mode and the current status of the counter. means once we have given the command, we can again read back, we can check that what is the program mode, what is the count value, etc. in the current mode. This is not present in 8253. Now coming on to the basic architecture of 8254. See, the basic architecture of both the ICs are same. So this diagram applies for 8253 as well as 8254, right? Now, when we'll see about the basic operation, we see over here that this is the counter number 1, that is known as counter 0. This is the second counter, that is known by the counter 1, and this one is the third counter known by the counter 2, right? 1, 2, 3. These are the three counters. And guys, which we have already discussed, each counter has got 3 pins. One is the clock, the second one is the gate, these two are input pins, and one is the out. This is an output pin. Again, I discuss in detail. Clock is something which is the backbone of the microprocessor, the pulse which is taking from the crystal oscillator. On this frequency, this counter works. Gate pulse is a command signal from the microprocessor to start the counting, and once the counting is done, it informs the microprocessor by an output signal, that is out. So clock 0 means clock pulse of counter 0, gate 0 means of counter 0, and out 0 means the out signal of counter 0. Accordingly, 3 each signals has been there in each of the counters. Coming on to the data bus buffer, what signal it does, we see here. This side is your microprocessor, where I am writing from the marker mu p, and from here the data travels from D7 to D0 to the data bus buffer, and from this data bus buffer it comes on to this internal bus, and then from the internal bus it travels to the counter and reaches the counter. Why it reaches the counter? Because from this data bus we will get from the microprocessor the value of the count. Suppose we have to count back from 100 to 0, so this numerical value 100 will come to the data bus and will be stored there in counter 0, and once the gate pulse is received, it will start back counting from 100, 99, 98 and so on. Now coming on to this fourth block, that is the read-write logic block. This is the whole brain of this IC, the whole architecture controlled by read-write logic. How read-write logic works? We have got control signals like RD bar, WR bar, A0 and A1 and the chip select. It decides that which operation has to be done, read or write, and which counter is to be selected in counter 0, counter 1 and counter 2 accordingly. So this box, that is read-write logic, controls the whole operation of 8254. Then by the control signal we can see the last box, that is control word register, is being attached over here. This register is the automatic mode of this IC, where the value of A0 and A1 is 1 1, so this is selected. This is an automatic mode that it by its discretion will decide that which counter is to be selected. So these are all about the internal architecture, how it works. As you can see, the control word is further connected with the control signal with each of the counter, as you can see where I am marking here, and each of the counter is connected with data buses to the internal bus. Here comes the pin diagram of 8253/54. Coming on to the pin diagram, we find that it is a 24 pin IC, and starting from pin number 1 to pin number 8, we have got the 8-bit data buses, namely from D0 to D7. These are the data buses which we have already seen in the block diagram. They are directly connected with the microprocessor for receiving the value of count, and after counting receiving the value of delay. This one, the 9th pin, is the clock. From here the clock is received for the counter 0. Similarly, we have got clock 1 and clock 2 for counter 1 and 2. We have got out 0 means output of counter 1. Similarly, we have got out 1 and out 2 for the counters 1 and 2 respectively. Here is the control signal to start counting in counter 0, that is gate 0. Similarly, we have got gate 1 and gate 2 for the counters 1 and 2 respectively, right? Now this IC is powered by pin number 12 and 24, that is the ground and VCC. WR bar we are well acquainted with, that is if it is active low, the writing operation will start. RD bar is read bar, if it is active low, the read operation will start. And this is the chip select bar. CS bar is chip select bar. Once it is active low, then only this IC will be in read or write mode unless it will be there in high impedance. Means if we want to take work from this IC, this CS bar has to be in activated mode. Since there is a bar above it, so it has to be given active low for getting it activated. Now these are the two address control signals by the matrix of which we select the type of counter or the automatic mode. Coming on to the data bus buffer, which we have already seen in the block diagram. This is a tri-state bidirectional 8-bit buffer which is used to interface the timer IC to the system data, and it has got three basic functions. Programming the modes of 8253 means all the modes which are used, which we'll be discussing later, is programmed by this. Loading the count register, we have seen the count value goes and travels through the data bus buffer to the counters, and reading the count values. Once the counter is done with the counting, the out signal will tell that what is the value of the count value. So this is the last function of the data bus buffer. Read write logic, as we all know, this is the main brain of the whole IC. It is the control logic unit. It includes 5 signals. We have already seen there in the block diagram. So these all are our nodes for us now. RD bar, WR bar, CS bar, A0 and A1. And in the memory mapped input output mode, these are connected to MEM R bar and MEM W bar. These are the memory read and write operation. Coming on to the address lines, as I have told, A0 and A1 forms a matrix of 0011 to select which type of counter we have to done. And CS bar is tied to a decoder address. Now what is the control word register they are selected? We'll see in the next slide. This is the slide I was discussing. This is the slide which tells A1 and A0 how they do. If both are 00, you have to make a note that A1 comes first, then comes the A0. 00, it's counter 0. 01, it's counter 1. 10, it's counter 2. And if both are 1, this is the automatic mode, that is control word register. Control word register now uses its brain to select which counter based on the priority. And if both are at high impedance, there will be no selection. Coming on to the control word register, the main control word register is the controlling register of the whole IC. It consists of 5 input signals, that is A0, A1, RD bar, WR bar and CS bar. And you can see by these 5 input signals we have created a matrix of 0 and 1s which tells that what operation is to be performed. For example, whether it is the write operation, the first 3, whether it is a read operation, the later 3, and whether it is a no operation which is reserved for the future use. And if the status is 11100, it is the write control word which we have already seen as an automatic mode. Now we'll discuss the most important and the last one, that is the operating modes of 8253. Basically 8253 or 54 can operate in 6 different modes, and we will discuss in this slide in detail. So the first mode which is there, it is mode 0. And what are these 6 different modes? Mode 0, mode 1, mode 2, mode 3, mode 4 and mode 5. Now what is mode 0? It is interrupt on terminal count. What is a terminal count? The last count which is done to terminate the operation is known as terminal count. What is mode 0? It is used to generate an interrupt to the microprocessor after a certain interval. After some interval it will generate an interrupt, no problem. And initially the output is low, and after the mode is set, the output remains low after the count value is loaded in the counter. So we all know, till the time it is not loaded into the counter, it remains low. The mode 0 is still continued. What it says, the process of decrementing a counter, see over here, the process of decrementing the counter continues till the terminal count is reached, right? Terminal count means the last one. The count remains 0 and the output goes high and will remain high till it loads a new count. So the new cycle will start. Mode 0 further says the gate signal. Gate signal means the signal which starts the physical counting. The gate signal is high for normal counting, and when gate goes low, the counting is terminated. Terminated means it is stopped, and the current count is latched till gate goes high again. High means active high, the 5 volt, right? Now coming to mode 1, that is programmable one shot. As we guys all know what is a one shot, once it is triggered and it is not repeated. It is very similar which we see in 555 timers, the very similar operation similar to monostable multi-vibrator mode. It can be used as monostable multi-vibrator because its name is one shot. The gate input is used as a triggered input in this mode, and the output remains high until the count is loaded and a trigger is applied. I repeat, the output remains high until the count is loaded and the trigger is applied. Coming on to the mode 2, this is also known as a rate generator, where the output is normally high after initialization. As soon as we initialize, the output is normally, most of the cases, it's high. And whenever the count becomes 0, another low pulse is generated at the output and the counter will be reloaded. This is a crux over here. Whenever the counter becomes 0, the count value becomes 0 when we have done all the counting. Another low pulse is generated and the output counter will be reloaded. Coming on to the mode 3, this is a square wave generator. What is special about the square wave generator? The timing of the high and the timing of the low is exactly same. Then only we can create a square wave. So this mode is similar to mode 2, except that the output remains low for half of the time period and high for the other half of the time period. Both the time periods has to be equal. Coming on to the mode 4, that is the software triggered mode. This is the very famous mode. Any mode or the triggering which is done during the program, the software which we have written, that is known as the mode 4 or the software triggered mode. What happens in this? In this mode, the output will remain high until the timer has counted to 0, and at which time the output will pulse low and go high again. I repeat, it will go high again. Then what is the next point? The count is latched when gate signal goes low. So we have to remember, latching of the count is done only when the gate signal is low. Low means it is connected to the ground. On the terminal count, the output goes low for one clock cycle and then goes high. Terminal count is the last count. When we are finishing the counting in backwards, the output goes low for just one clock cycle and then goes high. This low pulse can be used as a strobe. Strobe, you all know, that is a control signal. It can be used as a strobe. Now the last mode, that is the mode 5, and this is one of the most important mode also. This is known as the hardware triggered mode, right? What happens in this? Why is it so important? This mode generates a strobe. A strobe, as I have already told, that what is in a strobe over here, guys? This mode generates a control signal, that is the strobe, in response to an externally generated signal. Hardware triggered mode is something where The strobe or triggering is done from some hardware parameters, your power supply, your jump ring, your short circuiting, or your time delays, your external peripheral delays, or your external peripheral interrupts. These all are known as hardware interrupts. What are hardwares? Which we can see, touch and feel, right? So this mode is similar to mode 4, except that the counting is initiated by a signal at the gate input. How the gate input is done? This is by any hardware triggered instead of software triggered. Hardware triggered is physical triggering, software triggering is in a program it is written to be triggered. After it is initialized, as we can see, after it is initialized, the output goes high. Very nice. And the last point is that when the terminal count is reached, the output goes low for 1 clock cycle. This we have seen in mode 4 as well. The terminal count is the last count. The terminal count is the last count. When it is reached, the output goes low for 1 clock cycle, and then again it goes high and the counting again starts, right? So this is all about the 8253/54 IC. Thank you for being so patient watching this video, and if you still have any query, any doubts, please write to me at my email ID ajay.sharma@united.ac.in. Now see you back soon in the next video. Thank you all of you.